to do today. So if PL and PMX are Legendre polynomial order L and M, this is equal to 0 for L not equal to M. Okay, that's the autonomy property. Normalization property is if L equal to M, which we'll do separately. These are the two things I would like to do today. L is equal to M. It's nothing but 2 over 2L plus M. Okay. So they can be combined into one property. That's what we normally would do, right? I mean, which is called auto-normalization property, would be -1 plus 1 P of x, Pmx dx is 2 over 2L plus 1 product of delta L comma M, right? We can combine the two into one relationship, which will be called as autonomial property. So for each special function, you'll have such things. The normalization, property, and could be, you have to find out what that is, right? In each Bessel and everything. Okay. So first we're going to prove this, and then we'll come to that one. So the property that the two things that we can do are, we know PL is a solution of Legendre differential equation. So it must satisfy the following differential equation. Right? This we know. My first goal is to prove this. All right, since I need PMX also for the polynomial of order M, I should have the following relationship. This much I can write. Can we combine these into one expression? I always ask you to notice this. This is the differential of coefficient is differential of that, right? If I have to combine these two into one expression using a differential, can we write it? How will you write it? I want that to write as d over dx of something. Okay.
D over dx of 1 minus x squared plus p of n, or p out of n.
P prime L? pre-prime Lx, right?
Yeah.
I can combine that into this, this way, okay. Any differential equation, this property called Sturm-Liouville, we'll come to that, but it has a very special property later on, okay, I can similarly, I can write this differential equation as d over dx 1 minus x squared e prime of mx, okay, plus n times n plus 1 given of x. Right? So I've written the Legendre differential equation in this form. So, I'm going to erase this for a minute. No, now we're going to write that down. All right. And I have to prove that, right? So I started with, with already what we know, PLX, PMX, which satisfy the Legendre differential equation. So in order to get to that, what should I do? Okay, let's just multiply with PMX. I need PMX definitely, right? So I can multiply this equation with PMX and this by PLX as a first step. Okay. So I just, it's outside this. Okay. And I can multiply this by PMX. Is it PMX or PLX? PLX, I should multiply that because I want PLX. Alright. So
on the top, should that have been PMX in the
what did I do?
beginning?
Yeah,
The
what did
first-
it was PLX?
PMX,
It's
the first
PMX,
term.
PMX, yeah, exactly.
Okay.
Multiply the first one by PMX, second one by PMX, okay? Because I'm trying to get that, right? And I want to get that order. Yeah. So the first equation by PMX, multiply. The second one, multiply by PMX. Multiply by P sub LX. Alright, so this is what we have. What else can we do? My goal is that. What other manipulation can I do? I need to get that in the, let's just integrate between -1 and +1, or, and then subtract one equation from the other, or all these things we can try to do, okay? So let us integrate this between -1 and +1, okay? Similarly, this between -1 and +1, and we are just playing with it at this point, okay? So the next step is that, let me do it here itself so that you can see how I'm trying to develop this proof. So let us integrate now this expression between -1 and +1, okay, and integrate with respect to x. Okay, I don't think I need it, but this is this point. Let's just do that, okay. And similarly, -1 to +1, PLX. Okay, this, can you do integration by parts? This equation and that, both of them. So if you want to do the integration by parts, what happens? Let's integrate this first because I have a differential already here, so it's easy to do that. So integration by parts. So I get 1 minus x squared p prime lx pmx minus 1 to plus 1, okay, minus negative minus 1 to plus m of all this quantity p prime lx, and I can take the differential of that, p prime of mx dx. Alright. So that's that term, and this one I'm going to leave it like that. So this is just this part I'm writing, okay? Of course I have that also. Maybe I can write it so that you just get plus L times L plus 1 minus 1 plus 1 PLX PMX dx equals 0. So this expression has become that. And similarly, this one will become what? I do this one, integrate that first, because that's under total differential. So it's easy to differentiate. 1 minus x squared p prime of mx p sub lx, integrate, evaluate this between minus 1 and plus 1, minus 1 of this whole thing, minus 1 to plus 1, 1 minus x squared p prime of mx. Now take the differential of this, p prime of mx dx. And I have all this other term, plus m times n plus 1 minus 1 to plus 1 PLX PMX dx equal to 0. Right? So this is what this expression has become. Right? What is happening to the first term? Goes to 0, both at the upper and the lower limit, right? Because of 1 minus x squared, it will become 0. So this term becomes 0. Similarly, this term is 0. Okay, but I have to prove that. This is just that top. Now, if these are similar. If I now subtract this from the other one, I can cancel that because they're exactly the same, right? So now what you do is subtract whatever we got, let's call it, subtract 4 from 3. So that will eliminate the other integral, okay? And then what we end up is L times L plus 1 minus m times m plus 1, this quantity, integral of minus 1 to plus 1, PLX, PMX, dx equal to 0. So that's a constant, we pull it out, and then I'm subtracting this from that. And then what we have to do is for L not equal to m, if, of course, if L not equal to m, this is not 0, so this has to be 0. So that is your optimum property. So this is why you have this. Right? So we started with a very simple thing. PL is a solution of Legendre differential equation, so it has to have this polynomial, Legendre polynomial of order m. You must have under different, should satisfy that. And then we made this expression into total differential, right? And that's it. And then we integrated this by parts, and these two things, go to 0 by itself. Then I'm left with this, which I cannot eliminate by itself. It's not going to 0. So I'm subtracting this from that one expression from the other one. I generated two expression, one in, when you multiply by PL, other one with PM. So when I subtract one from the other, I can eliminate that. Then I end up with these expressions, right? And the only remaining one would be this and that. Right? When you subtract, so that will lead to that expression. Is this clear? Okay. So it's a very simple proof. I mean, the only knowledge we had to have was, PLX satisfies the differential equation. The rest is simple stuff. Okay. Simple integration and clever manipulation. That's it. Alright, so the next one we want to prove is the normalization property. When L is equal to M, the normalization is that. So for this, I'm going to go back to our generating function method that we used last time. The generating function for Legendre polynomials is 1 minus 2xt. It's a function of two variables, right? Plus t squared to the power of negative half. This function of two variables produces a power series PLX, the coefficient which is Legendre polynomial, which is a function of x. It is a function of x and t, right? So all the function of t is here, and the function of x is in the Legendre polynomial. L going from 0 to infinity. That's what we have. That's what we proved last time. All right. I need to prove that, right? So again, this is my goal, and this is what I know, from previous lecture. So how do I get to p squared? First I have to get to p squared, right? I have PLX. What should I do? Given this expression, what do I do?
For both sides.
Square both sides, yeah. So if you square both sides, one minus 2xt plus t squared that's L, sorry. Whatever it is, same power, right? I'm going for. I can write it like this. Squaring the right hand side means it's infinite series is something like this, right? Because this, this is a dummy variable, so in principle it is something like this. All right. What can I do further? I need integration, right? we have to put p square Lx. So what's the next step? I mean, I squared it because I know there's some p square Lx or something I have to get, which I still don't have, but I may get it eventually. Okay. So what's the next step should we do? Just wild guess.
When ST equals 0.
Hmm?
I'm just talking nonsense.
I need to prove my right-hand side, okay. There's one more thing that we've just learned, which also we have to explore, right? We just learned this. This also we know, right? I mean, this is what we just do. Some of my right-hand side has to simplify, you know, from where it is, it has to simplify further, right? What are we trying to do? Integral, right? We want to show is integral between -1 and +1 of that quantity should be something. Can I integrate both sides? Again, between -1 and +1 with respect to x, not with respect to t, with respect to x. Can we do that? What happens here? Because you got two variables, so you have to integrate the right variable. So what happens to this whole thing? I'm going to write it and you have to tell me what happens to this. Okay. I'm integrating with respect to x. Okay. So I can put all these, each term has an L equal to 1, it's P0x, P1x, P2x is there. But we know the property, right? So what it means is, this summation, the only thing that survives is
Is when
L equal to N. L equal to N. So we have P, that's how you're going to get you're going to exploit an orthonormal property, okay? So L equal to N. So what is happening so all these summation, the only thing which is going to survive is L equal to N term. So I can write this whole expression as nothing but -1 to +1 dx, okay? What do I want to call P? If I chose L equal to M, P square Lx dx is there. And then what happens to the power of L? Can I write the whole expression like this? And what is here? Can I write this as 2L? L equal to N. That's the only term which is going to survive, right? And L equal to N. Okay, so let me just start. So what we have is the following now. -1 to +1, 1 over 1 minus 2xt plus t squared. That's your left-hand side. And the right-hand side has become the following. Integration is with respect to x. and I can pull, that means I can pull the tip of 2L outside, L going from 0 to infinity. And then I can write this as -1 to +1 e square Lx dx. This is okay? Alright, you know how to integrate this, right? What should I do for this? So eventually I'm going to pull, somehow extract this information by comparing the coefficient t to the power L on both sides. That's how we do it. You know, before doing that, I had to do more manipulations here. But what is the integral of this? The integral with respect to x. Can I multiply and divide with -2t? If I did that, you know what to do with this. Right. The integration with respect to x, so this is what? Natural log of 1 minus 2xt plus t squared, right? Evaluated between -1 and +1, and I got -1 over 2t also here, which is nothing but alright. So this is -1 over 2t, and we are substituting for x, right? I mean, so this will become what? Natural log of 1 minus 2t plus t squared minus natural log of 1 plus 2t plus t squared, which is equal to all this stuff. All right. So it's -1 over 2t, and this is what? 1 minus is a natural log of 1 minus t squared, right? Minus natural log of 1 plus t squared whole square. So this is nothing but 2 can be cancelled out. -1 over t, natural log of 1 minus t minus natural log of 1 plus t. That is equal to what I need. L going from 0 to infinity, t to the power 2L, negative t squared Lx dx. All right, what is natural log of 1 minus t? This is what I'm saying, function to series, series to function of sums. In typical functions we have to know. This is nothing but negative t square over 2, or 2, right? Yeah. Minus negative, so all that stuff, right? And what about this? Natural log of 1 plus t,
G minus T over by
t minus
T over by G
T squared.
over
2 plus.
plus T cube.
So it's that is alternating, and the other one is all the terms are negative, right? this should be equal to, and there's a negative 1 over t here, okay, equal to this whole stuff. Right now. Alright, so the negative, that's negative 2t. So it is this is plus and that is negative, right? I mean, so that will cancel. This is common to all of them, right? This negative 1 over 2 is common to both terms. So let me put this big, in other words, the confusion. So all the, this term is nothing but negative 1 over t. I have a minus 2t, right? That even term will cancel, plus, is that what it is? It's 2t, yeah, okay. The other one is, it's all of the negative terms. This is what you have. Okay, so that is nothing but 1 plus, I can take out the 2 factor out, right? T square over 3 plus t to the power 4 over 5 and so on and so forth, which is equal to that term. Now I need to put this back into series form, into summation form, and I should have a coefficient 2 to the power 2l, right, which I can do, right? So I can write this as what? This whole left-hand side, I can write as t to the power 2l, l going from 0 to infinity. I got a 2 definitely, right? Can I have it as 2 over 12 plus 1? Is this capturing everything? L equal to 0 is fine, 1 plus 1. L equal to 1 will be 3, L equal to 2 will be 5, right? And that will be that. So all I have is this. Now you can compare the coefficient of t above 2m on both sides. So compare the power of 2l on both sides. I can, if you want, I can put it here inside. So that means -1 integration of p squared ls between -1 and +1 is nothing but this quantity 2 over 2l plus 1, which is your normalization property, okay, that we wanted to do. So all we did was, here we exported the generating function property, that 1 minus 2xt t plus t squares, square root of that, inverse square root of that, generates a Legendre polynomial. We just squared both sides, and step by step we wanted to know what we wanted to prove, and we had to integrate both sides with respect to between -1 and +1, right? And then always the trick has been going from function to series and series to function. That kind of a trick we have done. And in order to get whatever we want, we have compared the same power of t or x or whatever it is to extract whatever the information that, in this case, integral that we wanted to calculate. So I want you to understand the big picture of how we did step by step, right? I mean, so that way you can do it. So here the only thing is, yeah, that you need to know a few things like how to expand natural log of 1 plus t or natural log of 1 minus t or 1 over 1 plus d or 1 over 1 minus t kind of things. Some of the function, how you can expand in terms of series. Okay, so those are the key things. All right. The next thing that I want to do is actually, yeah, Rodriguez formula. It's nothing but, it's a differential representation for so that's what it is. So it goes like this. Legendre polynomial of nth order is nothing but nth derivative of following quantity. I'm going to prove this to you in a minute. Is nth derivative of x squared minus 1 to the power L, 2 to the power of L, L factorial. You can see this is useful because you can calculate again. I mean, we had recursion relation. If you p naught x, you can calculate p1 and p2x through the generating function that we had. Now here, if I know, you can calculate any order of Legendre polynomial because this is the expression. So you know p1x. If you did that, it should give you x, right? I mean, it already gives you normalized Legendre polynomial. It also gives you that. This expression. So p1x, just all we have to do is L equal to 1, right? 1 over 2. Okay, which is 2x over 2, which is 1, right? Similarly, you can calculate p2x. What about p0x? 2 to the power of 0 is 1, L square, L in a 0 factorial is 1, right? What does this mean?
Don't take the derivative of the x squared
Minus 1 to the power of 0. Anything to the power of 0 is 1, so it is 1, okay? So don't take the derivative, okay? If your constant will be 0, right? Don't take the derivative and then x squared minus 1 to the power of 0. Anything to the power of 0 is 1. So this is 1. So I just want p naught x is a bit tricky, but others are just normal derivatives you can do it. Okay. So I want to prove this expression to you, and it's also very useful one. So again, to prove, you can see something I have to, nth power of something I have to prove, right? So So let us start with this. Let me start with the function u, which is nth power of this quantity. Okay, so define some variable u, which is a function of x, which is x squared minus l. Okay, and let's start looking at it. First derivative we want to take is what? N x n minus 1, right, times 2x. It's nothing but 2 times l x squared minus 1 l minus 1. This is equal. And since I can write this as what? This expression I can write as u prime. Think of multiplying by x squared minus 1. Actually, I'm trying to get rid of that, basically. 2 lx x squared minus 1 of l equal to 0. Okay. So multiply x squared minus 1, so in this becomes x squared minus 1 upon l. And x squared minus 1 upon l is nothing but my u, the original function. So I have this expression now. U prime x squared minus 1 minus this one. All right. So I need from here, I have to somehow get to all these things. Okay. All right. How many people remember Leibniz formula? Remember that when we practice? Okay, I need to get to this. Okay, I mean, so I have to differentiate this expression several times. I'm going to say that let us differentiate this expression. This point here. This is what I have to do, but my problem is, I mean, I got product of two functions. I mean, this is also function of x, right? This is also function of x, this is x, right? I mean, so what Leibniz formula, we're going to use this at this point. If you have a function f of x, let's say, which is product of two functions, okay, and I want to take nth derivative of this function. So the formula is the following. Nth derivative of such a function is given by the following formula. N prime, n factorial, sorry, r factorial, n minus r factorial, this function, which I call, I'm going to use this notation. This means rth derivative, okay? I mean, it's not power of r. This is a, so that I don't want to get confused with powers and all that. So this notation, let me just write down, r going from 0 to n. So this notation that I'm using, this means rth derivative of u. And this one is n minus rth derivative of e. Okay, that's what this means. Okay. So if I want to differentiate this expression of L plus 1 times, I want to see what I get, right? So let us first do this a little bit slowly. First, basically I want this, right? That's what we're trying to do. x squared minus 1, what is apply Leibniz formula, and then I'm going to apply this also to the other one, and then subtract, okay? Should I take 12 also here? Okay, let's take it so I don't forget it. Although it's xu which matters, but and subtract, okay? What happens to this? Okay? So this is first derivative, okay? So what do we do with this? What is n? N is L plus 1, right? Nth derivative, I will need L plus 1 of the derivative. So that much at least is clear. Or we do it term by term. Let me just tell you, a trick for in applying the Leibniz formula is we have product of two functions, right? We need to choose which is u and v because this is going from 0 to n. I want this to terminate quickly, okay, the series to be terminating quickly, okay? So if I chose my function u to be x squared minus 1, I know it'll, after two derivatives it's going to be, it's going to stop, right? And similarly, u I want to take as x in the other one because I don't know when the other one, if I have chosen u as u prime, I don't know when I cannot terminate it, right? I mean, so that way this L plus 1, otherwise it will have L plus 1 terms, right? I mean, 0. I want to terminate this as quickly as possible, okay? So if I chose in that formula what I call it big U, which is not same as that, okay? If I chose big U to be x squared minus 1 for this, right? What are the different terms? I have the first term is what? N plus 1 factorial, okay? 0 factorial is 1. It is N plus 1 factorial, so that's 1, right? The first term is that. And I said I'm going to take that as x squared minus 1. Okay. Again, r equal to 0. This is a derivative, right? I mean, so which means don't take the derivative. I'm going to put that, otherwise we'll mess up. It's not power in this case. It means don't take the 0th derivative. V for me is what? X squared minus 1. V is u prime. So I do need what? U prime, n minus r, n is L plus 1, right? This is really effectively L plus 2, okay? L plus 2th derivative, okay, of u, okay? So I'll come and correct, so let me write down all the terms and then, or maybe if you want, we can do it right now. I'll call this as L plus 2th derivative, okay? Because I'm now absorbing that, of that term. Plus r equal to 1 will have what? L plus 1 factorial. This one will become what? L factorial, right? And then u, now I have to differentiate r equal to 1, first derivative of that will become 2x, okay, of this, okay? And v is u prime, n minus r, so that is what will become n is L plus 1, right? L plus 1 minus 1 is L, so this whole thing is L plus 1. Okay, you can also see the pattern emerging, L plus 1th derivative of u. All right, so that is my second term, and the last term would be similarly L plus 1 factorial. R is, this R equal to 2 term, right? 2 factorials should be there in this case. And L plus 1 minus 2, which is L minus 1 factorial, correct? L plus 1 minus 2 is L minus 1 factorial. And so the next term is 2, derivative of this. And you can check, it will be Lth, the last term will be Lth derivative of u, right? Because v is u prime, L plus 1 minus 2, so L minus 1, so u prime will become L derivative. So I'm going to simplify this for you. So this expression is simply x squared minus 1, right, L plus 1th derivative of that, and this is L plus 1. This is L plus 1 times 2x times, I'm going to write it, now we can write it a little bit nicely. So 2 and 2 will cancel, it looks like here. So it is L times L plus 1. Is this clear? I mean, we're just going term by term here. All right, what about the next one? What should I write? In this case, I'm going to take my u to be x, right? U to be x, v to be u. So this will have only 2 terms, unlike the other one which had 3 terms. So n equal to, the first term will be 1, okay? So fine, L plus 1, 0 factorial, L plus 1, so that, so the coefficient is 1. U is x for me, of 0, which is, don't take the derivative. V is u, and then n minus L plus 1, L plus 1 minus 0, so L plus 1 of the derivative, it looks like, right? Plus, next term is what? L plus 1 factorial over 1 factorial over L factorial. I think it is, just check my L plus 1 factorial divided by 1 factorial L plus 1 minus 1 L factorial. So it's L plus 1. Okay, so just making sure. Okay, that's L plus 1. And then u is, now r equal to 1, so it is 1. We have taken the derivative. And v is u. And what is that? L plus 1, right? L plus 1, sorry, r equal to 1, L, sorry, L of the derivative. The next term will be 0, okay, the constant term is 0. So there are only 2 terms here. So x to power, don't take the derivative means x, right? Okay, this is what we have, okay, which I can write as 2L x, L plus 1 of the derivative u, plus 2 times L plus 1, Lx derivative of v. Alright, so this is my second term. And I have to subtract this, subtract this from that equation, right? This is L, we are taking L plus 1 as derivative of this expression. I just took the derivative of this and derivative of that, and I need to subtract. So when I do that, what do we have? Let's see, simplify this further. So I have the leading term. What do we get? That is x squared minus 1 u, L plus 1, L plus 2th derivative of u, I will get. And here I'm going to subtract it, 2lx, so that will cancel with that term. So all I'm left with is here plus 2x u, L plus 1th derivative of u, alright? And here you have so I do have minus L times L plus 1 u to the power L equal to 0. So if I multiply by 1, negative 1, this becomes 1 minus x squared u L plus 2 derivative minus 2x. All right. does that remind you of? Can I write this as 1 minus x squared, b squared, dx squared, e to power this quantity, right? Minus 2x. That's what it is, right? I mean, so if this is the case, what can you, starting with that u equal to x squared minus 1, this is what we are getting. So what can you say about u, nth derivative of u? I mean, that's what u of, parenthesis L that you have written is nothing but nth derivative of u, right? So what can you say about that quantity? What is this quantity?
It's also a solution.
Hmm?
It's also a solution
Of what?
of the Legendre differential equation.
So it's Legendre polynomial. Okay, so what I'm trying to say is whatever that quantity we have written is nothing but Legendre polynomial. Right? Because Legendre polynomial will satisfy that differential equation. That's a Legendre differential equation. So u sub L should be proportional to Legendre polynomial of L. We can make that claim, right? So and u is that, right? U is, this means what? Nth derivative, right? This means of u, that's my notation, okay? And so this says nth derivative of u, which is x squared minus 1 to the power of L, that's how we started with, is proportional to p sub L. I can write as some constant CL. Okay? So we get part of it. I mean, we know that the nth derivative of this function that we had is Legendre polynomial, but this constant factor we still have to get. Right? I mean, at least we know this quantity is proportional Legendre polynomial. That's what we have proved at this point. Now, in order to get this last part, so what is CL? I mean, of course it has to be that, but we have to prove that, right? What property can we exploit of Legendre polynomial that you know? Is there anything that you can exploit to get this coefficient? What are sequence and properties that you know Legendre polynomials?
The integral of it from -1 to 1 with L squared needs to be equal to I'll find my notes in a
One,
second.
yeah, yeah. But that's a bit complicated. We have, I need to get something. So that may be maybe a possibility. If you can prove it, that's good. I'm going to do it a simpler way. Okay. Yeah, I mean, yeah, then I have to integrate that, whatever it is, and it's not really, maybe you can get it.
It sounds like a bad idea.
It's not a bad idea. It's not at all a bad idea. That's a good property. Yes, absolutely. Yeah. I'm not saying it is not. Yeah, I'm pretty sure you can get it. Okay. Absolutely sure you can get it from there because we already have, that is equal to 2 over 12 plus 1. You understand? I mean, maybe there is a way. Is there anything else? I'm going to differentiate this left-hand side several times and check what happens to it, okay? Now. But then I need to know something about the Legendre polynomials on the right-hand side so I can get CL automatically. Do you know when does it become 1? I mean, there are a couple of times, I cannot say P0 at this point because then it gives me only C0. I want for L. You know that P of L for x equal to for any order of Legendre polynomial for x equal to 1 is 1. Okay, that's one of the properties that we had done. Okay. For the normalized Legendre polynomial, that's what we used. Okay. So we know that P of L, regardless P0, P1, P2, at x equal to 1 is 1. This part of property only. Can I exploit that? Because then I can make that as 1 and then evaluate this whole thing for L equal to 1 eventually. Okay. So let's see what happens if I do the first derivative of that first. Then I have what? L and nx minus 1, and then I have 2x. We just see a couple of terms, okay, then I'm not using Leibniz or anything at this point, just to again simplify before that. I think n minus 1, I have that, I'll have 2x squared, right? And I'll have one more term here, right? This is the first derivative only, right? n minus 1, 2x. Okay, then I will have the other term, which is 2l, when I take the derivative there, x squared minus 1, minus 1. And when you differentiate this L times, you can see that this term will become, this will become L factorial, right? And this one will become, this term which is not derivative, it will become 0, x squared. Okay. And this perhaps is going to become 2x for L. And all other terms will have something of L x squared minus 1 first time, okay, and some coefficient, okay. Then you have x squared minus 1 square something, some term, okay. All these infinite series will be there. So when I try to evaluate that for x equal to 1, for x equal to 1, what happens is this side is Cn, right? What happens to this left-hand side, all other terms will be 0 because it has this x squared minus 1, except this, because this is to the power 0, which is 1. So you will have, my left-hand side becomes L factorial 2 to the power L, and all other terms will drop off, is equal to Cl, because P of Lx is equal to 1. So this one is nothing but 2 to the power L factorial, so P sub Lx is nothing but what we have written down. Right? 640, yeah. Okay, so you can see this is useful again to generate Legendre, polynomials of high order. And again, for different special functions, you have different kinds of representation. Bessel function is an integral representation, which is also very useful because in optics you use that representation quite often. Okay, and it will prove useful in this kind of expression, useful in I think both quantum mechanics and electromagnetic theory. Okay, so these are some properties of each specific function has some important properties that we have to know so that we can apply wherever it comes. Next time, what I want to do is Bessel differential equation, and we'll talk about other special, gamma functions and stuff like that. So you have exam, test one is on Tuesday, right?
Next Thursday.
Next year.
Thursday, not Tuesday. So you got full 1 week, huh? 22nd, yeah. 22nd, okay. So I will finish up Bessel differential equation definitely, up to that. That's what you will have, test one, okay? And today I'll give under homework, so that you can practice other things. So tonight I'll, give under one so that, please look at the blackboard. I mean, I'm not posted it yet, but at some point tonight I will post it. So that way you are a little more comfortable with these methods. It's a methods at this point, right? So what you have done is so far learning how to solve second order differential equation. You say the ordinary part is the front half of the and the other one is what's it called? From is it Frobenius, because I'm thinking of Bessel function, I'm thinking of Frobenius fraction. Frobenius series, those are the two things. Wronskian method, if you know solution one form, or we calculate the second solution. Wronskian method. What else we have done? And of course, just started doing special functions like Legendre polynomial stuff. You can forget about a partial differential equation at this point. I mean that will come later on. So separation of variables method you don't have to study for this test number one. Just start studying from second order differential equations. Okay, the methods, different ones that we have learned. So that's what we cover. So
The coordinate systems.
you don't have to do that at this point, because that will again be, it's connected with the PDEs, so we are going to revisit that later on. So you don't have to just start from second order differential equation, because that's the part that I want you to study. I mean, if you want to start preparing for it, I just want to let you know. And so you have to know how to set up the initial roots root equation. If you get the equation, you at least have to know how to do it. It's the lowest power of c is equal to 0, right? I mean, that's the term that you're looking for to set up the initial root equation. So, so perhaps, lecture 3, second order differential equation, lecture 3. So just focus on that. So it's a methods course, so you must be ready to, derive things and stuff like that. Just know how to expand 1 over 1 plus x, 1 minus x, binomial expression, natural log of 1 plus x, natural log of 1 minus x. These, because we are all the time converting function to series to function. So just refresh your memory about all these things. Okay. All right. So we'll start next week in Thursday. We'll discuss Bessel differential equation and gamma functions and stuff like that. That's a way to represent factorials. Actually, gamma function is a way to represent factorials, especially if it is not a factorial, which is not integer factorial, half factorial, 3 halves, or negative half factorial. How do you represent that? That's why we have gamma function, because that will appear in Bessel function basically. So I'll talk about that. Both these things I'll talk about next time. Okay, let's stop here. Any questions for the homework? Everybody's comfortable with the homework? I mean, it's fairly simple. I mean, straightforward, I think. Right?
gosh.